Can you steal information from a quantum system without smashing the interference fringes that prove it was both ways at once? In the energy filament theory, weak measurement works because you insert a deliberately shallow stake into the energy sea, strong enough to bias the statistics, but too gentle to force a full, irreversible closure into a single labeled path. A strong measurement is basically a hammer. It couples hard, pushes the system over a readout threshold, and leaves a loud recording in a memory chain the environment can carry forward. Once that record exists, the two roots become physically distinguishable, and the fine phase texture that makes fringes gets shredded. Weak measurement is the opposite attitude. Touch, don't grab. You couple so lightly that the system is only nudged, not pinned. Your pointer shifts a tiny amount, but on any single run it is drowned in noise. So you can't honestly say, it went through slit A this time. What you can say after many runs is, this setup makes the pointer drift as if slit A had slightly more weight under this weak coupling. That's the whole trick. You trade certainty per trial for gentleness per trial. Think of it like checking the wound with a feather instead of an anemometer bolted to a tower. The feather won't give you a clean number on one flap. You need many flaps, many seconds, a lot of averaging. But the tower instrument changes the flow around it. And in a delicate system, that back action is the whole story. Eft calls this out bluntly: measurement is coupling, plus closure, plus memory. Strong measurement forces closure now, and writes memory clearly. Weak measurement delays closure. It leaves only a faint tendency mark that becomes readable only in the statistics. This is why weak measurement often comes with post-selection, which sounds mystical but is just bookkeeping. You make a gentle probe, then later you sort the data by a final condition, like keeping only the receipts from one store, and the conditional average can look strange. Textbooks named that a weak value, and people started talking like the particle secretly had a bizarre hidden property. Eft stays boring in the best way. You didn't uncover a secret label. You chose a filtering rule that amplifies a tiny bias that was always statistical, and fringes. They don't magically become immune. The moment your weak tag becomes even slightly usable as what path information, fringe contrast must fade. Because usable information means the memory chain could. In principle, sorting runs into two bins. You can even erase the tag by choosing a basis that makes the label indistinguishable again. And then fringes can reappear in the right grouped data, not because you rewound time, but because you changed what distinctions can be written into memory before closure. So weak measurement isn't cheating physics. It's choosing an exchange rate. Pay a little coherence per trial, pay many trials per bit, and accept that you're buying an average, not a path to confession. Tap follow, share it on New Physics, Clear Universe.